Oh, hi everyone. Can you hear me?
Yes.
Yeah, I think now I might. Okay, I'm very thrilled to have you guys here in this special session. So focus on traffic flow advancements and some autonomous vehicles. I think this is the first time we bring such topic into the BTR conference, so we're very excited on that. I think we're due on time and everyone here. So for participants that are here, please note that this is a special session on traffic flow, so we're gonna commence soon. Uh, I, me, myself, and Yanping, we're gonna be monitoring the chat box here as well. So feel free to, chat, drop your questions there, engage with the audience, and we'll be monitoring this and soon. So given this is, of course, a special session focused on traffic flow, it is, by no coincidence that Professor Jorge Laval is with us today, and we're going to commence with his first lecture. So Professor Jorge Laval is a professor at Georgia Tech in the Department of Civil and Environmental Engineering. He got his PhD from University of California, Berkeley, working with Carlos Daganzo. His research focuses understanding multiple elements of traffic flow theory, as well as complex system theories and machine learning. Some of his recent work and contributions has been identifying challenges that machine learning suffers when it comes to urban network control and how can we improve autonomous vehicle control models. Other contributions are estimating macroscopic fundamental diagrams and stochastic car following models that allow for statistical inference. So we're really thrilled to have Jorge Laval with us today, and please, the floor is yours. Please go ahead.
Thank you, Wissam, for that kind introduction and for this invitation. I'm thrilled to be here and talk about our latest research. This is done by my co-authors there, Garyan Lee, who's recently graduated, so this is part of her dissertation, and Ariman and Kurt, who are physics colleagues here at Georgia Tech. All right. So our recent work has focused around the idea of complex systems. All right. And so the first couple of papers you see there are kind of the foundations that we've come up with. And today I'll be talking about universal scaling laws. In freeway traffic, you can access, so it's under review, but you can have access to the archive paper right there. The big deal about this paper is it's the first one to validate these ideas around traffic flow, that it's a complex systems with data. And we're going to use the I-24 motion data set. I don't have to describe it a lot because you and you will do that in the next few sessions. All right, so as a motivation for this work, the main idea is that the complex systems are just full of power laws or scaling relationships, right? Of the types you see here. So these are very relevant to transportation, where you have the annual delay on different cities in the world, right? So we start with US cities and the very left there. But our recent work shows that this is true all over the place, right? So you see it all over the world. You see these scaling laws, right? And these scaling laws just says that the delay in this case is proportional to the population raised to a power. Okay, so these power we call critical exponents in this theory. And if there's one idea you want to think about complexity science, if you will, is that they're all scaling laws like that for some reason that is very profound. So all these systems are kind of the same mathematically, and all right. So the scaling exponent here is 1.2. That's not good news for our daily lives, because it means that if you move to a city with twice the population, then your delay will go up by more than 2. All right, so that's not good, right? So it gives us ideas or ways to try to make resilience better in transportation systems. All right, so before I run out of time, let me give you the main messages of today's lecture or presentation is that traffic flow is a critical phenomenon. So it's governed by the scaling laws, really. Right. So if you're familiar with the phase transitions, right, when we boil water to from liquid to gas, that's a phase transition. In the case of transportation systems, it's from free flow to congestion. Those are the two phases of the same matter, if you will. Right. And what plays the role of temperature, it's going to be the flow, the input flows of our networks. Right. So the main results of our research is that traffic has this universality that we call self-organized critical, SOC, and also KPZ, which is another universality class that I'll be talking a little bit about, right? So everything, as I said, is a power law. In particular, we'll see that the sizes of the jams is a power law, right? So you see there the survival functions, so probability the jam is greater than something S is again a scaling relationship with that exponent, right? The total delay on a city, as we saw as a function of population before, when you express it as a function of the system size, L, so you would see that it's scaling with that exponent 3 divided by 2, right? And then in traffic flow, we also talk about, right, the cumulative count curves. So it turns out that these count curves, when you accumulate across space, so the integrated density, if you will, they look like random walks or Brownian motions, right? When you're at this critical state, right? And we see that in the data. Another implication is that the fluctuations of this cumulative count curve, for example, the standard deviation or variance or any moment, they grow as with time or space in predictable manners, again, scaling laws, right? And finally, probably the main message for this community is that all these properties are captured by the simplest traffic flow model of all, which is the kinematic wave model with triangular fundamental diagram, right? But you need an extra ingredient, which is a small white noise. So a small perturbation, a small random noise. So deterministic is not going to do it, but if you want the full picture, you need to add some random noise, right? Which is good news for modeling because this is, again, the simplest model, and we've been studying it in this field for decades. All right, so this is the data set we're going to use. Again, I'm not going to describe it in the interest of time, but we're going to use these 8 days that are freely available, or just say available for researchers around the world, right? So what you see here is of course, heat maps of speeds, and you clearly see the shock waves um, in the freeway. All right, so what is universality? Is kind of an umbrella for all these things as you see here, right? So these are very different systems, right? But in common, they have that at the macroscopic scale, they're governed by these scaling laws that I've been showing to you, all right? So near the critical point, in the case of networks, the critical density, all these systems look the same statistically, right? So the distributions, etc. All right, so these universality classes come into flavor equilibrium. So you can think of the fundamental diagram of the MFD, right, which are equilibrium kind of variables. They obey the same scaling laws across cities. What I'll be talking about today is the non-equilibrium case, right? So the dynamics of traffic. I'll be talking about SOC and KPZ classes. All right, so SOC, self-organized criticality, the best mental picture is this sand pile model experiment, right? So you see sand coming from the top there, and all of a sudden you're going to have avalanches, right? So in a freeway or in a network, right, it's the sand would be the cars joining the network, and then at some unpredictable point, you would have these traffic jams propagate. Right, and that's the main example of self-organized criticality, which the main characteristic is that these are systems that are naturally attracted to a critical state, right? And traffic is like that, right? This is because, for example, the outflow of a bottleneck is always the capacity flow, which is the critical state, right? So it's a natural tendency to a critical state, which is not good news because they become unpredictable and not easy to control, right? And here you see the probability, the survival function that I've shown you, right? And you see that the linear part is what the exponent would describe this scaling relationship. All right, so we proved this self-organized criticality of traffic and this paper that you see here a couple years ago. What I want you to take away from it is that we see the same distribution of traffic jams here that we saw for the sand pile model, right? The slope of -1/2 here for the survival function, right? So these traffic jams are the colors you see here in this time space diagram, right? These are places in the time space diagram where vehicles are stopped or going at very low speeds, right? So you know them probably have shock waves or stop and go waves, right? So the area, the size of these in the time space diagram, right? Their distribution is a power law with the predictable exponent of 1.2. So this is for the kinematic wave model with triangular diagram again, with random walk initial conditions. All right, so that's kind of the stochastic aspect of it. All right, so from the data, how do we get these clusters or traffic jam clusters, right? So we start with the trajectory data, which has holes, right, overpasses and whatnot. So from there, we calculate a mean speed field, which is the discretized version, right? So each cell would have a single speed in it. And then we binarize that field, right? So if the speed is less than a critical speed, then we would say that it's a zero. If it's less, it's a one, right? So we focus on the jams, right? If it's greater than this critical speed, it would be a zero. And then what you get after is these clusters, these jam clusters. So these clusters defined by a series of contiguous ones, if you will, right? So cells where traffic is bumper to bumper, right, under this critical speed, and that all these cells are connected to one another, right? So that defines a cluster. All right, so that's one part of the evidence. So we take one of these days and then use a critical speed of 10 miles per hour. You see these jam clusters in different colors. All right, so these are your stop and go waves, but again, binarized. And each color is because they're different clusters, right? But then the survival function that you see here, right, this probably that the size is greater than little s, would have a linear relationship in this log-log plot, right? Yeah, so I forgot to mention all the plots are log-log coordinates, right? Because then the slope of these lines will give you this critical exponent, right? So the slope of the line here is -0.53, right? But we'll be talking about actually the critical exponent tau in percolation, which is actually 1 plus that slope, right? So this is consistent with the kinematic wave model, which again, the slope was 0.5 and the sine pound model, right? And that's the evidence. All right, and we find this for all days and surprisingly for all speed the threshold speed here, as I will show in a minute. All right, now it has to be said that since this is a finite data set, right, only 4.2 miles, or it's the largest so far, but right, so we don't see the full extent of these jams. So you see that they keep propagating, but we don't see them, right? So there's a cutoff, this cutoff cluster size. Right, so this power law is true up to some cutoff because then you have what we call the finite size effect. So, right, we don't see them. So we have to estimate what that cutoff is. All right, so that's the cutoff variable that we have to estimate from the data. But according to the theory, it scales as well with the system size L with this fractal dimension critical exponent df. All right. Another one we calculated is the fractal dimension of delay, which is this d here, which turns out to be around 1.5 as well. Right. So delay, as we saw in the beginning, right, scales with the system size in this way. All right, and we found a hyperscaling relationship relating all these three exponents. Okay, now here I show you that these power laws are true for a wide range of these threshold speeds VC. Right, so you see this linear relationship again on the survival function is kind of true for all speeds between 10 and 30 or 35 approximately. Right. So, and that's another characteristic of self-organized criticality. It's a natural tendency to be in the critical state, so you don't need to fiddle with the parameter in order to get these power laws. Right. So of note is that within this range, there's two special points. So the first one is the point where these jams span the whole system, right? And then at around 25 or so, these gems start to coalesce or to propagate laterally, as you see here, right? They start to merge. And that's because of lane changes near the on-ramps of the freeway, right? But nonetheless, so even if you have these different dynamics, you would have the same type of linear relationships here. All right, so very quickly, so this summarizes kind of what we measured. I only focus on these three critical exponents. We measure many more in the paper, but just focus on tau for now, right? And you see that it's pretty stable with respect to this critical threshold speed, right? So between 10 and 30 it's approximately constant, equal to 1.5. The other is the delay critical exponent. Right, which is also around 1.5, maybe goes up a little bit after that, but overall they're pretty stable exponents. All right, so that's the self-organized criticality part of traffic. Excuse me. Now let's quickly talk about KPZ universality. All right, so this is actually a handwritten note by Cardar, which is the K in KPZ. And this is from the 80s, actually, right? So he has the question, what are the following topics have in common? So you have growing interfaces, shock waves, traffic flow, optimized paths, vortex lines, etc. Right? Answer one, nothing at all, which is what you would think at first, but actually, yes, the answer two is the correct one, and is that they all exhibit fluctuations governed by the same generalized diffusion equation. Right, and what it means is that you're going to have this equation. We're not going to go into much detail, but the behavior of this equation they found is just governed by these three exponents, the alpha 1/2, beta 1/3, and z of 3/2 that we've been seeing before. All right, so at the basis of this theory is this height function, h, right? Which in traffic flow terms is the cumulative density, right? So you take a picture of the freeway and just cumulatively count the vehicles, right? As a function of space x. And do you interpret that as a growing interface, right? Which is what you see here. So it grows from T1 to T2, it kind of grows in this way. Now, this is the KPZ equation, and on the first paper we showed at the beginning, we show that it comes from just the existence of a fundamental diagram, right? So this is the fundamental diagram, if you will, and then we add viscosity and a stochastic term to it, and you get this. Now, what's interesting here is that back in the 80s, they had the hunch that traffic flow is part of this universality class, right? but this is the first time we prove it with data, right? There's no other effort in the literature. It's all been theoretical or by simulation of traffic models. All right, so very briefly, if a system is in KPZ class, then this W, which represents just the standard deviation of this cumulative counts, right? So again, you take a vertical line there at some given time and just count the vehicles and analyze the time series, just get the standard deviation and see how it varies in time. Again, in log plot, right, you would see that there's this predictable increase of the standard deviation with a slope of 1.3, sorry, of 1/3. Right. And this is the type of universality, right? So it's a very different system from all the others, yet the fluctuations, they grow in this way. All right. And then just very quickly here, the other test we typically do in KPZ is the correlation function. Right. Again, you take the same spatial series at a given time, and you analyze the correlation of 2 points separated by a distance r. And then if you plot this in these rescale coordinates, you should see a slope of 1/2, which we see from the data. All right. And by the way, this 1/2 is what tells you that these cumulative counts obey the random walk type of stochastic process. All right. And yeah, let me just leave you with these main messages that I already gave you, and also with some ideas for improved congestion management there. The main thing here in congestion management is that instead of focusing on deterministic thresholds, like exceeding a capacity value, etc., one should monitor the scaling relationships, right? So these fractal dimensions or these exponents, as they do in financial forecasts and many other, right, complex system kind of theory settings. All right, and with that, I'll be happy to take any questions.
Thank you so very much, Jorge. We'll open the floor for questions. So we have a question from the chat. I can speak it out from Yan Ping. So are the scaling laws still valid in mixed traffic scenarios with varying levels of vehicle automation?
So I can only guess that yes, they will be. Now, as I understand, in the next version of the data set, they will be releasing data with autonomous vehicles in it, so we will know for sure. But again, my guess is yes, because these models, right, they have very few assumptions, and the main assumption that is the most important is the idea of the exclusion principle, which mainly says that you don't want to bump into the car ahead, right? So you cannot be in the same place at the same time. And that is going to be true for any type of vehicles, right? Be it autonomous or not. So we don't want to crash. And just because of that, I would think that the same scaling relationships should apply there.
I have a question out. So from this idea that we should actively steer the system away from self-organized criticality, but there is like a notion of randomness in behavior or unpredictability when it comes to self-organized criticality. So isn't some interventions that we do might have unintended consequences on traffic? So we're kind of forced, we're in this loop of doing some active role in the system, but then having unintended consequence.
Right. Yeah, and that's the thing about these systems. If you're at the critical point, it's very finicky like that, right? So anything you do could have unforeseen consequences, right? So one simple control strategy would be like we're doing, like perimeter control should be effective. Preventing the system to get to the critical point. Now, the problem is that that critical point is variable, right? As you suggest. And there's no single, critical density that you should stay away from, right? So what this theory tells you to do is instead of focusing on that, focus on the scaling exponents. Like the 1/3 parameter of the standard deviations, for example, which seems to be more robust. So it doesn't change, from day to day so much as the critical density would, right? So that's kind of the idea there. And so in traffic, we're used to maximizing the flow, right? We call it the sweet spot, right? To be near the critical density so as maximize the flow. That actually could cause more harm than good in this theory, right? Because then you're pushing the system to be in the critical point again, where jams of all sizes could happen, which is the meaning of these power laws, right? Is that you can expect jams of all sizes, right? Smalls or ones that would propagate the whole system. Yeah.
We have probably time for one more question. So Sharath asks, has the scaling relationship been validated in complex road networks?
In what type of network?
Complex road network.
Not sure what you mean by complex in this system, but I'm guessing, yeah, urban networks maybe.
Yeah, yeah.
Yeah. Excellent question. So yeah, there's a large body of literature, especially from cities from China where they have a lot of data. And so at the network level, urban network level, they find scaling relationships. Right. So like the gem clusters, right? So they find similar behavior of the gem clusters across the whole network, right? So it's the percolation universality class, which I didn't talk about today, right? Which is kind of in the same area. So yeah, this is true for a freeway, a single freeway stretch, as I showed here, but also for urban networks.
Okay, I guess our time is up. Thank you so much again, Jorge,
Thank
for
you.
this amazing
Thank you so
work and
much.
sharing this with us. Thank you. So next we'll move ahead with our next topic here. So we're very glad to have Rulin with us. Sorry, can you hear us? Hi, Rulin. Rulin is an assistant professor in the Department of Civil and Environmental Engineering at University of Southern California. She earned her postdoc in mechanical engineering from University of Berkeley and had a postdoc at Stanford University. Rulin also has been selected for as a rising star in mechanical engineering in 2022, as well as in civil engineering in 2021. Her research is on the design and control of future mobility systems, particularly involving autonomous agents. So I'll leave the floor for Rulin to share with us some of her most recent research.
Thank you, Wissam. Is my screen everything okay?
Yes. Yes.
First, I thank Wissam for inviting me today, and I'm very happy to share some of our recent updates on the research side in my lab. And the title of my talk today is When Altruism Meets Autonomy, Managing Waving Ramp Congestion with Strategic, Connected, and Autonomous Vehicles. So it's no longer the wildest dream that we see autonomous vehicles navigating on our streets, especially in Los Angeles. We can see more and more Waymo fleets operating on the roads, and perhaps in the very soon future, we see the Tesla fleets operating on the roads. And looking ahead, we're not just talking about isolated deployments of these autonomous vehicles, but also we're envisioning a future where a significant population of autonomous vehicles coexist with human-driven vehicles. And we refer this data as called mixed autonomy. However, today, autonomous vehicles still make up a rather small fraction of the vehicles on the road, and an even smaller fraction of travelers' mode choices. And this situation could be very challenging because we all know that human drivers' behavior can be spontaneous and hard to predict. So therefore, let's say if we have very limited number of autonomous vehicles among many human-driven vehicles, the uncertainty of the environment is rather big, and therefore it's very challenging for the control and the safety and the efficiency for organizing these autonomous vehicles. Compared to the future, where we envision that our goal is to have a rather considerable population of autonomous vehicles on the roads, at that time, we have many autonomous vehicles among several or a few human-driven vehicles. So therefore, the corresponding environment is relatively more controllable. And we can use these autonomous vehicles for better benefits for the whole society. So therefore, one of the key challenges that we face right now isn't just about getting more autonomous vehicles out there in the system, but it's more about finding the right balance and eventually pave the path among the goals of different stakeholders right now in the transportation system. For example, like autonomous vehicle companies optimizing their profit and cities trying to manage this congestion, expecting less cost and more revenue from the roads, and individual users like daily commuters that value safety or travel time. So to truly explore the potential of autonomous vehicles, what we need to think is to strategically about how to scale up the autonomous vehicles deployment in a sustainable and coordinated way, especially as they navigate and interact with the current mixed autonomy environment, which should be the case for at least several decades ahead. So as autonomous vehicles begin to enter our roads at scale, we need innovative new models that can incorporate not only their presence, but also account for their strategic interactions with the current main road users, the human drivers. And this isn't limited to a single setting. We see the interaction between the human drivers and autonomous vehicles everywhere. For example, especially in those game theoretic geometries across the traffic networks, for example, like roundabouts, merging and diverging zones, Vivian ramps, routing networks, and beyond. So therefore, in all these mixed autonomy environments, we encounter a recurring challenge. For example, the first question that we want to ask is, how do agents interact? The second question is, how do we model that interaction behavior? And then we want to ask, how can we influence such interaction behavior to make the system safer, more efficient, and more fair? These are the core questions that drive our work recently. So before I talk to the specifics of the interaction, I'd like to first show several very typical human driver behavior that I investigate in my research. For example, this is a very typical and very famous so-called last-second lane divers. As you can see, a vehicle abrupt into the traffic flow and just did this very dangerous inserting of the lanes abruptly without considering their impact of the surrounding environment. And this very commonly seen behavior in Los Angeles roads, the last-second exits, especially at the scenario of ramps. As you can see, such behavior is irresponsible, but it is very commonly seen and harming the surrounding safety and efficiency of the system. Even though those behaviors seems quite chaotic and crazy, the underlying reason for such behavior is that human drivers are selfish. By selfish, I mean they only care about their own goals and their own cost and benefits without considering their impact on other vehicles or the whole transportation system. Fortunately, in the future, if we have a considerable proportion of autonomous vehicles compared to human drivers that are usually spontaneous and uncontrollable, previous results in literature and experiments have shown that these autonomous vehicles can receive information more easily and subject to certain control more easily. So therefore, we can leverage the extra control that are brought by these autonomous vehicles. However, when we try to leverage the control of the autonomous vehicles to optimize for the societal transportation system, one thing that we want to pay attention is that due to the selfish nature of the human driver vehicles, these selfish human-driven vehicles may take advantage of such control. And these claims may seem a little abstract right now, but right now we are going to use one specific example, which is the Vivian ramp, as today's example to illustrate how the interaction and the taking advantage behavior and how possibly we can use the control of the autonomous vehicles to make the social traffic conditions better. And this is a recent work, joint work with two of my students. So the work is based on an example geometry, which is a Vivian ramp. So a Vivian ramp is, first you'll see an on-ramp, and within a very short range of distance, you will see an off-ramp right next to the Vivian ramp, and right next to the on-ramp. And the Vivian ramp is usually very complex because other than the traveling through flow, you will see the entering flow and the exiting flow. And all those kind of interactions happen in a rather short time range and distance range. So therefore, for such a Vivian ramp, even though right now we have a vanilla version where we have 2 lanes in the main line, but they exhibit quite high interaction complexity in terms of vehicle movements. For example, all those movements that are indicated by a circle, they indicate potential merging of different parties of the vehicles. And if we decipher such a complex interaction behavior, we can see that the movements that are colored by blue or black, they're totally goal-driven, which means for these vehicles, you cannot really control their strategic decision-making behavior because they have this goal. They either want to enter or exit the ramp, and you cannot tell them, like, say, you cannot do this, and you can exit at the next ramp. So basically, these movements are out of our control. But there is one kind of movement that can be controlled by us, that is the behavior that are colored by red. So those are the results of the strategic decision-making of mainline vehicles. Right now, we decompose this behavior into 2 options. So one option is bypassing, the other option is being steadfast. So basically, the mainline vehicles, when they are traveling along the mainline before the Vivian ramp, they project that there are going to be complex interaction ahead. So basically, they have 2 options. One option is that they bypass to the neighboring lane, for example, lane 2, and they try to avoid the congestion where it starts to propagate. And the second option is that they do is just they stay on the current lane. They either slow down or if there is any luck, they don't need to merge with any potential entering or exiting vehicles on lane 1. But in either way, we call the trays that are colored by orange the bypassing vehicles. And we call the trays colored by the blue the steadfast vehicles. So what we want to investigate is for a Vivian ramp like this, or for a general Vivian ramp, we want to predict how many vehicles will choose to bypass and how many vehicles will choose to stay steadfast at an equilibrium. And if we can model that accurately, the next step would be, if possible, can we possibly influence such collective strategic decision-making behavior to make the traffic conditions better? So we are inspired by a game theoretic concept that is usually used in the vehicle routing scenario on networks, which is called a wardrobe equilibrium. So basically, in our case, we consider that there is a cost function associated with the bypassing option and the steadfast option. And each of the vehicle, they will evaluate which cost is cheaper. And then they will choose the option with the cheaper cost. And we investigate their lane choice behavior from an aggregate point of view at the equilibrium, which means at the lane choice equilibrium, no one has the incentive to change their current choice. So basically, we can interpret it as a bunch of variational inequalities. Let's say at the lane choice equilibrium, if the bypassing option is cheaper compared to the steadfast option, then all of the vehicles that are traveling along lane 1, they will already have chosen the bypassing, which is the cheaper option. So on the reverse, it should also work. For example, if at the equilibrium you see no vehicles chose the steadfast option, then that must mean the bypassing option is cheaper than the steadfast option. So therefore, for a Vivian ramp, if we have the established cost models, we can use this wardrobe equilibrium model to calculate how many vehicles would bypass and how many vehicles would choose to stay steadfast in a very ready way. However, usually if it's a vehicle routing scenario on a network, we can use functions like BTR to quantify the cost or the delay. But for a specific scenario like this, the cost, we need to design for it. And here we only show the results of the cost design after our iterative design process. So basically, the eventual format of the cost is composed of two terms. So one term is related to the traversing cost, which is related to the movement of different parties of vehicles sharing a segment of lane for a period of time. And another term is related to the merging behavior, which is related to this behavior where multiple parties of vehicles trying to merge into one segment of the lane. And all those parameters, for example, C1t, alpha, beta, omega, C1m, they are determined by the later calibration and validation process by simulation data or real-world data. The exact values are out of our control. They are decided by the data itself. So every time we propose the cost models, and we need to calibrate those models with data collected from simulators or real world, and then we need to validate those models with another set of simulation data or real world data. And only if we have satisfying calibration results and validation results, we know that this is the right structure of the model, and these are the right values for the calibrated parameters. So if it doesn't work, if any of the chain of the process doesn't work, we need to re-propose another reasonable set of model structures. So on the right, we show the validation results of our model prediction, which are indicated by the red dots, and the true data that we collected from the simulation, which are indicated by the yellow dots. So our model predicts well. And more importantly, the model is excellent in terms of, in this case, we only need very few parameters to calibrate for each Vivian ramp. So basically, every time we only need a single digit number of parameters to calibrate to characterize a Vivian ramp like this. And the information that we need from this model are only the aggregate flow information, where we can easily collect from, for example, loop sensors right now on the roads. And even though in this case, the delay models right now, they are linear in the structure, but they can predict the nonlinear lane choice behavior of the vehicles in the mainline. And theoretically, we can prove that such an equilibrium always exists and is unique. So therefore, in the reality, when we have a Vivian ramp like this, we collect groups of equilibrium data to calibrate that, and then we change the situation of the Vivian ramp. We can still predict how many vehicles would bypass and how many vehicles would stay steadfast. And similar strategic behavior can be seen in different geometries. However, the cost structures are usually different. If there is any luck, we can try a couple of times, like for example, 10 trials, and we figure out the right structure of the cost. But in rather difficult structures, for example, like roundabouts, the structure of the cost is quite difficult to figure out. And the structure, sometimes it is out of our scope of knowledge right now, or the basic rules that we grasped from previous experience. So therefore, here we propose that we can use the current trained foundation models to come up with the available cost structures or search for the optimal cost structures in the feasibility space in an automated way. But back to our model. So the reason that we need to come up with this model is that we want to extend it for autonomous vehicles strategic control. And if we do want to employ such extra control of these autonomous vehicles, we better first make sure that there is a meaning for employing that. So therefore, we need to first examine whether such selfish behavior really harms the social traffic conditions. So what we do is that we use this metric, which is what we call social cost function, which is the aggregate delay of all parties of vehicles on this segment of Vivian ramp. And then we compare the socially optimal behavior to the model predicted or the true selfish behavior. So basically, the socially optimal behavior is a quadratic program, so which can be very easily to be calculated using the current software. And on the right, we show that the socially optimal behavior is indicated by the blue dots, and there is usually a gap between the model predicted behavior and the socially optimal behavior. So therefore, we do want to employ the control of these autonomous vehicles to make the social traffic conditions better. So how can we do that? So the first thing that we want to think about is, what if these autonomous vehicles, they're subject to a centralized controller? So this is a quite wild assumption that we are going to relax this assumption later. But right now, we assume that the lane choices of these autonomous vehicles, they subject to a certain centralized control where you can dictate before the Vivian ramp the certain proportion of autonomous vehicles to stay steadfast and certain proportion of autonomous vehicles to bypass. So therefore, we model that as a natural stackable game. So usually, a stackable game is kind of difficult in the computation and demanding it to converge. But luckily, in our case, the lowercase model for the human-driven vehicles is still the wardrobe equivalent model that we were introducing before. And it's not a very hard computation. So in our case, if we model the centralized dictation of the lane choices of autonomous vehicles as a stackable game, in the computation, it is acceptable. So we model these autonomous vehicles as centralized, controlled autonomous agents that serve purely altruistic decision-making, which means their single goal is to serve the societal traffic conditions, to make the social traffic conditions better. So therefore, corresponding to their centralized optimal lane choice behavior, the human-driven vehicles, they will still do this selfish behavior accordingly. And we analyze the impact of such control. One thing that we find out is that there is usually a stage where you need the proportion of autonomous vehicles to exceed a certain bar. And the reason of that is that the altruistic vehicle's impact must outweigh the selfish vehicle's exploitation. That is the selfish vehicle's taking advantage behavior that we were talking about a while ago at the beginning of the talk. And that may seem a little abstract, but here we borrowed an example from a previous example of the on-ramp. So in the on-ramp scenario, what we want to do is we want more vehicles to bypass before the on-ramp to leave more space to the on-ramp vehicles. So imagine if we control one of the vehicles, autonomous vehicles, to do this altruistic bypassing behavior, and as one of the human drivers following it. So even though previously we were thinking about doing this bypassing behavior, but right now we see a spot that is vacant in front of us. So naturally, out of our selfish nature, what we might do is just take advantage of this spot by staying steadfast. So this is one of the interpretation of the stage, why such bar needs to be, or the penetration rate of the autonomous vehicles needs to be met to activate their control in terms of the altruism. And previously, we were talking about the assumption that these autonomous vehicles, they're subject to a centralized controller to dictate their lane choices is rather a little wild. Because, for example, for Waymo fleets, they operate on the roads, but they are not socially optimal because they have their own tasks and companies are usually profit-driven. So they do want to optimize for their own benefit. So in terms of that, we propose a relaxed version of the altruism control, which is for selfish human-driven vehicles, they're still trying to minimize it. They're trying to minimize their own delay. But for these altruistic autonomous vehicles, we're going to configure the cost that they perceive from the roads. So basically, their altruistic cost is going to be a weighted sum of the previous selfish delay and a term that is indicating their marginal impact on the social traffic system. So one thing to mention is that if we incorporate that relaxation in decision-making of these strategic autonomous vehicles, then the model becomes a coupled wardrobe equilibrium on the right. So basically, each of the vehicles, they will have different costs to evaluate, but their costs are linked to each other or coupled with each other because they share the same segment of the road on the highway. And so therefore, in this case, if we try to weight the selfish delay and their impact on the social traffic system, so in this case, we don't want to dictate autonomous vehicles' choices, but we rather want to design a certain incentivization in terms of how much altruism that they can contribute and how much selfishness that they can preserve. And the work is still ongoing, so I didn't show the results in this talk, but basically, we'll still see the different stages in terms of this control. And the underlying phenomenon that is autonomous vehicles are taken advantage to an extent by the selfish human drivers can also be seen in such case of control. So therefore, VivaRamp is one example of a set of tools that incorporate a unified set of geometries or game theoretic geometries in traffic system that we want to show that autonomous vehicles can serve as altruistic decision-making agents, and we provide these updated models to incorporate such strategic control that involve autonomous vehicles. And here I'd like to advertise a bit about my new lab that established since last August at USC. So in our lab, we want to unlock the potential of autonomous vehicles, especially the population of autonomous vehicles in intelligent transportation systems. And on the transportation side, we also want to co-design the transportation infrastructure to suit or to seamlessly integrate these autonomous vehicles on the roads. And especially we are inspired by methods from game theory, controls, robotics, and artificial intelligence. So if you want to know more about our work, feel free to scan the code and get in touch by email. And that's pretty much all the contents for the talk today. Thank you.
Thank you so much, Roland. Very interesting research. So we will have probably 1 or 2 questions for Julian from the audience. If anyone has questions, please. So we have one question from user. Did you measure the congestion state and emission?
So how do I measure? Like, is it I'm asking like.
Feel free to unmute. Feel free to unmute and explain your question if you wish.
Right. So for the previous question, if the measurements, like, do I consider?
Can you hear me?
Yeah, we can hear you.
All right, thank you. So thank you for the presentation. I wanted to ask about if you measure the congestion state, the emissions across different penetration rate.
So if I interpret your question in a correct way, so correct me if I interpret it wrong. So in my model, basically the information that I need are flows. So the model doesn't apply in the situation where we have, for example, queues accumulating on the Vivian ramp. Like, we don't have a flow on the Vivian ramp. So if that's the thing that you meant for congestion, so that's my answer. And another thing, but my model does account for example, if it is like more congested on the Vivian ramp, but we still have the flow there. So that my model does capture that phenomenon. And for the emission right now, the social metric right now is more about the delay, like the mobility. So the emission right now is out of the scope of the current work.
Okay. Yeah. Thank you.
Yeah, I think we have one question from Kantara on why not use the traffic simulation with the DTA instead of fitting the delay functions?
So right now, so first, this model right now is a static one. So the reason that the underlying reason of this model, there is several fold of the reasons. But the initial reason that we want to develop this work is we do want to link the corresponding static equilibrium or the quality of the strategic decision-making behavior to the geometry of the Vivian ramps or the geometry of the roundabouts or other certain geometries. So therefore, it should have impact in terms of infrastructure design and related stuff, even before the policy is actually implemented. And so therefore, we do want to have a theoretical model. So then it can be generalized for different configurations of the Vivian ramp. So you feel free to interrupt me if you want to know more about the question.
I think so. Sorry.
Yeah, thank you.
Yeah, thank you. Our time is out, but Rulin, you have a couple of questions in the chat. Feel free to respond directly there,
Sure.
or read them through if you are able to. But yeah, thank you so much again, Rulin. Very interesting work. So we'll move ahead with our third presentation here by Junyi. Junyi, you can hear us?
Yes, I can hear you. Can you hear me?
Okay.
Can you see the screen?
Yes. So Junyi is a PhD candidate in the Civil Engineering and Institute of Software Integrated Systems at Vanderbilt University, working with Professor Dan Work. So Junyi has been a major contributor to the I-24 motion dataset that Professor Jorge Laval worked on for his analysis. Most of Junyi's work is on cyber physical systems and their application in freeway traffic. He also has been awarded the 2025 Rising Stars Award in cyber physical systems recently. So Junyi, the floor is yours. Please go ahead.
Yeah, thank you, Wissam. Thank you, Wissam and Yunping, to put together this special session in BTR. I think it's quite important topic, especially at current time. I want to take this opportunity of this presentation in memory of Professor Hani Mamasani, So before I get started the details of my work, I want to share a little bit story about Professor Hadi Mamsani on his impact on my research path. So back in the days on 2023, there is a traffic flow and traffic characteristic annual summer meeting at TU Delft. That time, that's the first time my advisor Dan went there and shared our analysis on the stop and go wave. And that time we are struggling with how to measure traffic and so on. And even that time we have a bad pronunciation. We call the Alice definition for traffic measurement. But Professor Hani Mamsani later comes to us and say, actually that's called ED. And he shared a rich story about those initiator of this whole direction, Leslie Eddy, Robert Herman, and Garzis, and so on. So that's right at the beginning of my research of my PhD, and it's opened my mind to the whole history of traffic flow theory, and so on and so forth. And also, just to mention the ED's definition, after Dr. Hani Mamsani's suggestion, we implemented correctly and share with the community. I think many of the users of item-for-motion data are currently benefit from the ED's definition for calculate the quantities for traffic. So I'd like to set up a little bit the mindset and the philosophy of our research is that I want to quote a saying from Robert Herman in 1992, is that we must continue to focus on the science of traffic, theoretical, experimental, and particularly observational to create a foundation on which we can build on the practical know-how that will allow us to understand the urban congestion. So that's a whole mindset is that we need to lean on this kind of empirical and observational data and then try to develop these kind of theory or methodology to explain the new phenomenon leveraged by the new technologies and even combining with some new technologies emerging in recent days. So I want to give a little bit of history about the research on traffic wave. So actually that kind of traffic wave analysis, it can date back to 1960s, the legacy of the Lincoln Tunnel. So that time, Leslie Eddy, he was the director of the New York Port Authority and is managing a couple of tunnels connecting to the Manhattan Island. So one of them are the Lincoln Tunnel and another is Holland Tunnel. From the empirical analysis, they find these two tunnels, some sort of the capacity is not as high as the other one. So then they start to put together a sensor network. That's, you can see the camera device back in that days. So the idea at that time is that they put a camera device on the roadside and put some tape sensors on the road surface. And then when a car passes through the tape sensor, then have a pressure, then you take a photo and estimate the speed. So you can see that's probably the first time-space-time diagram in history. Each dot in the diagram is a measurement for a car, and with the estimation for the speed. Then the contour is just the contour line drawn by this kind of speed observation in this kind of diagram. So also in the 1960s, the usage of helicopter is basically the experiment at Ohio State, the Interstate 71. That's the first time people in our community use a helicopter and fly with the flow and observe the traffic dynamics. It's actually a 4-mile trajectory data for about 5 minutes. And thanks to Professor Ben Kaufman at Ohio State University, he actually re-extract the whole data and digitize it and make it available. So these are all the efforts back in the days that people trying to understand congestion, and the stop and go wave are sort of the cornerstone of this phenomenon. So the next generation is a very famous NGSIM data in 2000. That's actually just a site by Berkeley. I'm amazed by the fact that you can actually see the I-80 section from NGSIM on top of the Berkeley lab. That's the latest advancement in this century. People start to use camera on roadside camera and embed with computer vision algorithm to try to extract the vehicle trajectories and then try to understand the micro level of this kind of dynamics. So the whole point, the whole idea of identifiable motion testbed is quite similar to NGSIM, but we just put this kind of idea at a scale of 300 cameras. So obviously it's a civil engineering project and need a lot of environmental evaluation, engineering design, so on and so forth. But thanks to the hard work behind this kind of design and construction, and in 2022, we launched this testbed in operation. As you can see, that's a sort of illustration of this testbed. We have 40 30-meter high poles along the freeway, and each pole, on top of each pole, we have 6 cameras. Each cameras are designed to observe one portion of the freeway so that later we can put together, have a bird's eye view of the trajectories. It enables the large-scale data collection and, most importantly, the experiments on the freeway. So the picture is a typical early morning day. We run experiment on the freeway, usually get out at 4 a.m., get rapid, and went to the site and do the control experiment, and so on and so forth. So to have an overview about how it really looks like is we currently have 276 camera in operations. So that's, you can see, if you look carefully at this video, you can see a truck move this camera, next camera, and so on and so forth. So ideally, we still didn't reach this point. Ideally, we can have complete trajectories from this testbed. That's what kind of current, we hope what current state-of-the-art computer vision algorithm can help us unlock this potential. Yeah, I mentioned the data quality now is not perfect. There are a lot of artifacts in the data, like the overparts of the bridge, some stitching problem issues between cameras. But still, you can. That's the first time we see a stop-and-go wave generated from our testbed. That's the first day of this operation of the system, and we feel excited because we only see this kind of thing in theory and in simulation. I think that's also the time that Professor Jorge Laval published his paper on on the complex system understanding of this kind of system. But that's really the first time we see that. It's really looks amazing, and when you overlay the sorry, it's a little bit. When you overlay the vehicle trajectories, which is an experimental car on top of this kind of space-time diagram, as shown in this figure is the white lines on top of the background traffic, that you can start to understand the interaction with individual vehicles and this kind of macro scale features that the stop-and-go wave. So I'm mentioning this because at the end of August 2023, we released the first data set from the system. We call it Inception. It's a 10 days of data set and with 8 days with congestions. But due to the fact that the data quality is not good enough, it's really hard for users to do those kind of microscopic, for example, calibrating a car following model and so on and so forth. So we take the idea of like, you have this kind of vehicle trajectories interacting with the macroscopic features and generate these kind of virtual vehicle trajectories based on the speed field calculated at a very high resolution, so that you can start to see how one vehicle start at the beginning of the test bed different times, how this kind of velocity profile of one virtual vehicle can experience among different lanes. Then you can start to look at that different patterns on lane 1, lane 2, lane 3, and lane 4. So everything here, I think I would say that's beautiful, and we are able to observe the wave, but can we measure the wave? That's a question. So a step further is that, can we develop a method to automatically identify all the stop and go wave boundaries from these figures? So I think that's just a basic walkthrough on the idea of space-time diagram. So all you see here is that you have an axis time and y space, and the car is moving. When it's free flow, we drop the green dot, and when it's transition to congestion, we drop the red dot, and so on and so forth. That's how this kind of visualization looks like. Actually, there are a whole bunch of data sets, either in the experimental setting, which usually on an open track, on a closed track with about 20 cars platoon, or with empirical data that you just put a sensor on the roadside and trying to capture the trajectories and see these kind of patterns. I think item4motion inception data hit a point of we can now analyze the traffic wave at a scale and the magnitude of thousands and the 10,000s of different waves and see which each wave looks like. So the fundamental problem here is that the traffic wave identification. So the setup is quite easy to understand. Given a space-time diagram and the critical speed, can you identify all the wave boundaries? And each boundaries showing here should be independent of each other. So at the very beginning of this research, we struggled a lot about how to say that's a wave, how to detect the wave. But we step back and look at the literature that Hani recommended to us, and we look at the Leslie Edie's research that he picked up a very simple definition about the critical speed. I think Professor Jorge Lava also picked up this definition for the critical speed for congestions. So we take this idea and but do that in a little bit different way on the vehicle trajectory level. So like here you can see that's the first vehicle trajectories, and the up is the time-space-time diagram, and the bottom is the time-speed series. And you can see these vehicles are slowing down and hit the critical speed, and we drop a red dot, claim that's a wave front, which means the time and space you enter the wave, and the drop a green dot that you leave the wave. We call it wave tails. And then you can have iteration of multiple different trajectories and this kind of definition. And you can see the wave like going to deeper, and so on. So you can play with this game, like draw a line and leave a dot, red, green, red, green, red, green. And so that we can have these kind of detections on the space-time diagram. So the funny thing and the very interesting phenomenon we see is that the wave we observe is not just propagate at the same speed. It can also propagate at a different speed, and one wave can bifurcate and merge to different wave, and there are some interesting phenomena here, like there is something like a river delta in the wave. I would say that's a wave in the wave, but it needs a representation. So here we leverage the idea of graph representation. So I'm going to give a very brief walkthrough. So like here, you can see from the right illustration, clearly these are two components, should be separated out, but this one on the left side, they should be connected, because this virtual vehicle, the wave didn't bifurcate, because in this case, two waves merged together. So I think we do this kind of the detection first and do the tracking on this kind of wave front. If that's the next vehicle's wave front is in a search region, we add to the list. Then we could have a tracking for the wave front, and same thing for the wave tail. And this kind of, because thanks to the property of the vehicle dynamics, you can always find a one-to-one pair for the front and tail. So like you enter the wave and leave the wave, you can always have an edge connect these two nodes. So that we can construct a graph and find the connected component from this graph. And that's some results we can get from that. So on the left, you are looking at the contour with Y dots for the critical speed of 15 miles per hour. And we can detect the wave fronts first, and then identify the wave front as components. So like here, there are multiple wave fronts, and then we can do the same thing for the wave tails. And then for the edge to connect the inner vehicle connections, then we can start to merge the wave front and wave tail together, so that we can start to represent and analyze these kind of very beautiful topologies of this kind of phenomenon. So at the end of these scalable analysis tools, we can now we are in a state like we can analyze the wave travel speed, travel distance, travel time, wave topology, when and where the bifurcation and the merge happens, and when and where this kind of wave generation and the dissipation happens. I personally believe these are all very sort of deep questions we haven't fully understand. It could unlock more understanding on this kind of nonlinear phenomenon based on this tool, and then we can take a closer look at what the microdynamics and the macrodynamics looks inside those kind of bifurcation and merge point. So the point of this tool is just to enable this kind of analysis, but that's quite important. Otherwise, there is not a systematic way to tell this kind of critical spatial temporal events. So like you can see, that's the lane 1, lane 2 topology. The topology is really rich and beautiful. I enjoy it a lot. So I did a very simple clustering strategy. So basically put the wave travel distance and the number of bifurcation of each wave and the number of merge of each wave, and put a k-means clustering, and that's how it looks like in the clustering side. So as you can see, the cluster result shows that the wave can be very simple and can be very complicated. So the example you see here is a wave travels 4 miles, but no split, no merge. It's very simple, straightforward, just growing. But for the other example, that this wave also travels like 4 miles, but it split for 4 times and merged back for 3 or 5 times. And I want to show you the most complicated one from this analysis is like I don't know how to explain why it happens, but it's really new and interesting to me. I would definitely wish to hear more feedback on this work. That I think it can be a community effort to really understand this kind of nonlinear, unstable wave dynamics in traffic. So for the purpose of making this kind of result more accessible by the community, I create a gallery of traffic wave dynamics. You can scan the QR code here, and it's a web page, and it's interactive. You can click on each dot, and you will see this kind of style wave dynamics for further checking how it looks like. Finally, more data is on its way. So it's sort of a comparison about the spatial temporal size about different data. That's inception is about 10 days, and we are going to kick off 50 days release later this year. It's 50 days of data, same size on space and time. It can unlock some potential application about the generative AI model. Like this is another research. I don't want to spend too much time. Just really interesting to me that we leverage the conditioner diffusion model is a generative architecture that condition the generation on the conventional sensors, like the loop detector. And then you can really leverage the resolution of the observation. Like you can clearly now to see this kind of wave dynamics. I believe it can be very helpful for the traffic management center to tell users when and where this kind of wave at an extreme high resolution. So thank you all for listening. Thanks to my collaborator, Professor Benedetto Piccoli, Yanbing Wang, Derek Glaudman, Sergey Zahar, William Barber, Jonathan Sprinkle, and my advisor, Daniel Wok, and many other collaborators to build up and make this testbed in operation. Thank you all. I'm happy to take any questions on this interesting topic. Thank you.
Yeah, I think that from Yanni, there is a question about if the cluster, the large number of verifications is due to the choice of the critical speed.
You mean the number of the bifurcation or things like that?
Yeah.
I didn't do this kind of cross critical speed consistency check, but I do have a sensitivity analysis in the paper. You can look for the details in the paper, but I want to explain it a little bit. So I would argue the bifurcation things happening. So like you are stopped in a freeway and the car in front of you already started. then you created sort of the spacing. So no matter what kind of critical speed you choose, this kind of bifurcation phenomenon is still there. So like you are distracted by a phone, for example, and then the spacing in front of you already started, then you think the spacing are good for you to reach a speed that can escape from the congestion, but it's not. Then all the following cars are experiencing two waves, not just one wave. That's how this kind of bifurcation would connect it to some daily driving experience from my understanding.
Okay, thank you. Do you have any more questions from the floor?
One more question from Professor Benjamin Koifman. Could the number of bifurcations reflect synchronization or non-synchronization across lanes? Perhaps it is moving faster in one lane, but then lane change maneuvers pull it back together. Yeah, very interesting point.
That's possible. I think it's to understand the synchronization, I think it's good for us to check the different lanes, this kind of dynamics of the wave. Are they at the same page, like the space and time? I think it need more investigation, and I agree it can be connected to the explanation for the synchronized flow. But I haven't done that. I like these directions. I'd like to explore more in the follow-up work. Thank you, Ben.
I think we can take one more question actually as well. So Jason asks in the chat, are there any characteristics of the roadway or traffic that leads to more or less bifurcations that could possibly make them more predictable?
Yeah. So I did an analysis on the spatial distribution of this kind of bifurcation points on the freeway. So you can clearly see there is a relationship between the ramp location, especially the merge point, and those kind of weaving area. It will lead more bifurcation events. But for some areas without any impact of ramps and so on, there are still bifurcation. And the merge happens. So I would say this event is not just related to geometry. It can also connect it to some other human factors in the system.
I think our time is up. Ginny, thank you so much for your presentation.
Thank you.
I can attest also to the to your website. It's so much fun. I played around with visualization. It's really recommended to look at, and it's very much fun. But Ginny, there are more questions in chat, so please free to look at and interact there. Thank you so much. Next, our presenter is Yiru Zhao. Yiru, can you hear us? Hi,
yes, I can hear you.
Great. So I know it's probably late night at your place. So Yiru is currently a PhD candidate at the Delft University of Technology. She has a bachelor degree in industrial engineering, and she's currently as well a PhD candidate. So Yiru works on mostly research at aiming for safer traffic for all modes of road users, utilizing automated technologies, which include but are not limited to automated vehicles, data-empowered traffic monitoring, and data-driven improvement of transportation systems. So we will be looking at some of her most recent work on safety and naturalistic driving. Yeah, please go ahead. Yeah.
Thank you, Wisdom. Thank you for the invitation and the introduction. I have a question before I start. I think we don't have enough time if the session is limited to 2 hours for the next presenter. Do I need to reduce my time?
Yeah, I don't want to stress you much on time, but yeah, we'll probably be a bit more over time. That's fine. So I just feel free to go through your presentation as smooth as possible.
Okay, that's good. Thank you. Then I would like to start. And so my name is Yiru Zhao, and you have heard the introduction from Wisdom. I need to move it a bit smaller. Today, my presentation is actually the latest work of my PhD and actually the last work of my PhD. And it's quite large, and the topic is learning collision risk proactively from naturalistic driving data at scale. You can see many keywords in the title, and that also means I will cover a lot of aspects about proactively collision risk quantification. But because we don't have much time, so I will make just a brief introduction of the whole, let's say the overview of the work, and then I will refer the audience to my paper, which include more details. Then let's start the presentation. The first, before I start, I have a question for everyone here. That's where do traffic crashes happen? Before I started doing the statistics work, I was thinking maybe highway has the most crashes because the speed is high and people usually drive with less attention when the driving is for a long time. But the fact is surprising. So if we see the statistics, only less than 6% crashes happen on highways. And more than 2/3 of them are actually in urban areas. And among the crashes between road users, which means we are excluding single vehicle collisions and those with parked vehicles, we see clearly that more than half of the crashes happen at intersections. And among the crashes at intersections, we also see that lateral interactions or angle interactions in the United States way are the majority of all the crashes. You might be curious, what are lateral interactions? Let's see here I have some examples that you might see. Let me use my lasers. So here we see this figure. It's generally longitudinal interaction, can be carpooling or sometimes a little bit lane changing. But at intersections, we have many more types of lateral intersections. They are of different angles, and you don't know where the other surrounding vehicles come from. Or you can see it, but you never know how you will interact in the next step. And just in these cases, we have much more crashes than in the longitudinal interactions. So today we're talking about proactive traffic safety, which means we don't want to wait for crashes. So we want to do something prior, or we want to do something before they happen. A collision seldom stems from a single catastrophic mistake. And generally, or very often prior to crashes, mild and severe traffic conflicts escalate. If you know something about the traffic safety, or if you're more familiar with traffic flow theory, no problem. I will introduce the pyramid. So safety pyramid is proposed in, I think it's many years ago, by Hayden, and then I think almost all the traffic safety researchers accepted this structure of analyzing crashes and conflicts and interactions. So basically the idea is that as we go from bottom to up to the safety pyramid, the more severe the events, the less frequent the events, which means we see a lot of encounters when we are driving or when we are moving on the roads. Then we see less potential conflicts, even less severe conflicts, or even real crashes. But in the opposite, crashes are most severe, which means we will have loss. Either it can cause either fatalities or injuries, or just some property damage. A collision in this structure is the endpoint of a series of crash precursors. This gives us actually some chances. For proactive traffic safety, we have two levels of view. The first level is individual or microscopic view. It's more about collision warning. So we know that there are many crash precursors and they are recognizable. This can give us the chance to save time for prevention. This can be done by either ourselves or the automated systems such as automated drivers or automated vehicles or automated driving systems running by a centralized center. And on the other level, we have the collective or microscopic view. In this part, more researchers are looking at crashes and crash precursors at a statistical view. They think that, okay, the numbers of conflicts and the crashes are associated. And this relationship or this association can help us evaluate whether infrastructure is good enough, safe enough, and also can inform us about policy improvement. So essentially, on both levels of view, the core task is to detect the conflicts, or let's say we need to estimate collision risk. And this is a task that not only traffic safety researchers are looking at. So in traffic safety research, I think most of us are familiar with surrogate safety measures, which are some physics-informed indicators to inform that there might be a potential crash. And in other fields, like in robotics and computer vision, researchers are looking at collision risk estimation in the other perspective. For example, in the robotics or in the control field, researchers usually make predictions of trajectories or reachable sets of movable agents, either pedestrian or vehicles. So because the trajectories and reachable sets are uncertain, then they propagate the uncertainty across the trajectories in the future. Then they will see whether there might be a collision in the future. So that's this is their way to measure or quantify the collision risk. And later I will explain what's the disadvantage of the methods. Then in computer vision, I think it's from 2018 that we have seen a lot of success from computer vision field. And that's why they also had interest on traffic accident anticipation, which is the same as our task of collision risk estimation, but their way is that they treat the task as an anomaly detection task. They use supervised learning or unsupervised learning to detect the vision patterns before crashes, so that they can detect the anomaly before it happens. Here I have a table about their features, let's say. In this paper, we will focus on 3 characteristics which are important, because if we want to employ collision risk quantification in the real world, we need context. Firstly, context awareness, which means for an indicator or for a quantification method, we don't want it only be specified to one condition or to one interaction type. We want it to be we want it to utilize all the information. So generally, surrogate safety measures utilize physics in information. For example, the speed, the acceleration, let's call it motion kinematics. And robotics persons also, except for the motion kinematics, they sometimes include other surrounding information. For example, the road layout or the other surrounding vehicle or pedestrians motion states. And then computer vision use more general, just the video information. So in regards of context awareness, that is how much information we can use to quantify the collision risk. The robotics way and computer vision way are okay, but traffic safety way is, let's say, disadvantageable. Then let's see the second feature of generalizability. By generalizability, I mean, if we train a model or if we have designed a model, we want it to be used for not only the specific situation, we want it to be generalizable in the other situations. For example, in traffic safety, we very often we use the time to collision, which is, I would say, very effective in car following situations. But if we want to apply it into lane change interaction or turning interactions, it fails. So generalizability of surrogate safety measures is not that good, and it's because surrogate safety measures are mostly specifically designed for one or two situations. And the generalizability of robotics way and the computer vision way are not good either. And this is a limitation of the machine learning itself. When you are training your model, either trajectory prediction model or traffic OTAA models, the training data has its own distribution. And once you move the model or you apply the model to another distribution of test data or application data, then you have the high chance to fail. Then the last feature is about scalability. Because collision risk quantification is, let's say, a key aspect of traffic safety. then we would like it to be applied in general for all the situations with a lot of data. But that's not always the case. For surrogate safety measures, its scalability is good because it's physics informed and we can apply it in, although it's not always good, but we can always apply it to almost all the situations. And then for robotics methods, because it's also a trajectory prediction, which means you don't really need crash data or near crash data for training, then the scalability is also good. But for computer vision models, they generally require crash data or near crash data as the labels. And for such supervised learning, it really limits its scalability because in reality, we don't have, and thankfully, we don't have that many crashes or near crashes recorded. Do we have a new solution? And as I see it, so today my presentation and in the rest of the presentation, I will introduce a generalized surrogate safety measure, which performs good at all of the three features. The core assumptions of GSSM, the generalized surrogate safety measure, is that conflicts are precursors to collisions, as well as continuation of previously safe interactions. This assumption is because we have introduced the safety pyramid, so this is a widely accepted assumption. And we make the pyramid flat, and we can use spacing as a proxy to measure how close they are or how intense the interaction is. The second assumption then is in the same interaction context, we assume that reduced spacing monotonically indicates increased risk. That's also aligned with the safety pyramid, because if we see that one triangle or pyramid is in the same interaction context, the closer the two vehicles or road users, the less safe they are. Then we have this curve, and the problem becomes we have a lot of different interaction contexts. For example, when we are thinking about carpooling, lane changing, there are two different interaction contexts. But if we focus on carpooling, different speeds of the vehicles can make new different interaction contexts. Even when the speeds are the same, if they are at different acceleration or if they are in different road segments, all this information in the surrounding or on the roads can make the interaction context different. And in different interaction contexts, we have different definition or we have different patterns of how close is unsafe. So the core problem here is that we need to measure the context condition spacing patterns to quantify the collision risk or to quantify the level of unsafety. How did I solve that? So to measure or to quantify the context conditioned spacing patterns, I used the Bayesian formulation of collision risk. So I will explain the equation step by step. I will not delve into too much on how I developed the equation. So here it's only about what does it mean. If we want to learn this, if we want to estimate the probability of a potential collision C based on the yellow part, it's spacing, spatial temporal gap between road users and other observables X that can be measured to describe interaction context. Here, the key is that X can include everything that you can think of or everything you can measure or observe. This makes a whole, let's say, a complete description of the interaction context, and then we can use data-driven methods to estimate the probability. So you have seen that in the Bayesian equation, we have 3 conditional probabilities, and 2 of them can be combined. And these 2 actually means when we so theta here is some latent representations, and when we combine them, the single probability of Px P5 condition on X, which means in a certain interaction context described by X, we use phi to describe the conditioned spacing patterns. Then we can infer the probability by a neural network. And the neural network can include a lot of information. We can have time series encoder to encode the speed profile, your angle profile. We can also have current state encoder to include the all the motion states, and we also can include lighting, weather, road surface, such qualitative conditions. And then based on this probability, because it measures the general or normal distribution of spacing patterns, then we can measure how extreme a current interaction is. The extremity or the extremeness of the interaction then help us quantify the collision risk. The more extreme interaction is, the more unsafe it is. I really don't have much time, so I will not explain too much on how the equation means, what the equation means, but then I will show some results. So here in this slide, I was planning to show you how I got the GSSM, the indicator from the probability, which is simple, but the key here, we can just see this sentence. The GSSM is operationally defined as the critical conflict intensity of an interaction described by the spacing and other observable quantities. So from an intuitive view, if the interaction involves a conflict, GSSM quantifies its minimum possible intensity. It's essentially also an indicator. And smaller spacing corresponds to larger GSSM and higher risk of collision. When GSM is equals to 1, which means the spacing is a median spacing under context X, then it means just a normal interaction. And when as the spacing is 0, which means GSSM would be infinite, and that's a factual collision. One important aspect I want to highlight is that GSSM, because it's generalized, then it means all the indicators or surrogate safety measures that is based on spatial temporal gap is a special case of GSSM. It's like an umbrella that all the surrogate safety measures are under it. Then finally, I would introduce the validation experiments. Because we have highlighted that the features of GSSM is accurate, which is basic, and then it's applicable across datasets, means generalizability and scalability, then context awareness. To achieve that, I designed the experiments to be across different datasets. So these different datasets collected in different countries and by different equipments, they are just for training. And for test, we use real crashes and near crashes, which are from SHARP2 dataset. And for comparison, we compare GSSM with existing two-dimensional surrogate safety measures, which utilizes the motion states of road users. Then I would really show the results or the amazing results. The first part is about how accurate it is and how in time the warning is. The figures shows that it's a bit complex. So the figures in this figure, the ROC figure, if the curve is close to this point, it's the best. For the PRC figure, if the curve is close to this point, 100 and 100, it's the best. Then we can see that the GSSM curve basically covers all the other curves. That means it has the highest accuracy with fewer false alerts and also less missed detection. Then in the figure of ATC curve, the horizontal axis means the median time to impact, which means how much time in advance the warning is issued before the crash. And then the vertical axis means the accuracy. So the higher when at the same accuracy, we expect the time to impact longer. We can also see that GSSM is doing the best in this curve. Then we need to talk about scalability. So the first part is we expect that the more diverse data are fed to the neural networks, the more accurate the GSSM is. And that's true. The second part is we expect the more information are considered, the more accurate is the GSSM is. So by information here, we mean it considers motion states, acceleration, environment information such as weather, lighting, road surface, and also historical motion information in the historical time series of trajectories. Then we also see that across different groups, we see that the more information considered, the more accurate GSSM is. Then it's the last table about context awareness, because SHARP2 it's a really nice data set that in SHARP2 all the crashes and near crashes are classified by their event types. We have rear end crashes, crashes or near crashes in the adjacent lane, crossing, turning, merging, and across all the events, JSSM has the best performance of accuracy and timeliness of warning. So you might be curious what JSSM is, essentially. It's actually, if you heard about safety field or risk field, it's actually just a quantity of collision risk. And in different situations, different location, different interaction context, it changes. Then I will play the video so that you will see. Let's see, can I play it? You will see that every minute or every time steps here it's 0.1 seconds. When the interaction context changes, the quantification of the collision risk changes. And here we see that GSSM is related to the spacing patterns and the probability of a collision risk. Also, in the last subfigure, you see that all the information here, because we are using a neural network, we can derive back to see what factors are the most important are most importantly influenced the estimation or the quantification. I already run out of time, but I still want to highlight the limitations of JSSM. So the first is its scope. You have you might have realized that JSSM does not apply to all collision risk. For example, for single vehicle collision or collision with infrastructure, it cannot handle. It's because JSSM is focused on interaction-induced risk. Then it's about the efficiency. When we are using a lot of data, when we are training a model with naturalistic driving, which of a lot of amount, then efficiency is a problem. And when we want to include more factors, when we want to consider more factors, more information, and build more complex neural networks, the more slowly the computation efficiency would be. And the last is about scalability, because neural networks is stochastic, statistical. Then even trained on the same data, if we don't control the random seed, we will get different estimation for each row. And the continuous improvement would be required in the future, because interaction behaviors also change when we are developing new technologies, when we are implementing new policies. So I would not highlight on its implications anymore, but you can see that if we can flexibly estimate collision risk, we can do a lot of things. It's beneficial for autonomous driving, for traffic management, and for emergency management. Then the last, I think this one is important, that I show the QR code here, where I open sourced all my code, and you can also find a preprint there. Which included much more details about the work than this presentation. And yeah, I think that's it. I will leave the recap slide here so that if you want to ask some questions, I can go to the slides. Thank you.
Thank you so much, Yiro, for your presentation. I think we're running a bit very tight on time, so we're gonna jump fast into our last presentation by Zihao Li. Are you with us? Zihao?
Yeah, I'm here.
Oh, hi, Zihao. So Zihao is a postdoctoral researcher at Texas A&M. He did his PhD at Texas A&M. Zihao's work is in multiple areas in traffic flow theory, connected automated vehicles, and cybersecurity. So I leave it for Zihao to share with us our final presentation. Thank you for
see my screen?
Yes.
Okay, so howdy everyone, my name is Zihao Li, and thanks for having me here and to allow me to introduce my research on the CV control and also the cybersecurity issue in transportation systems. So today's presentation topic will be the ERIFY-CAV, evidence-based resilience integration framework for connected automated vehicle control under cyber attack. So this is the outline for today's presentation, including introduction, method, experimental result, and conclusion. So we know the CAV system is a very, very typical cyber physical system, including like a cyber components like V2V communication and also control strategy, or we can also call it control algorithms. We also have a physical component such as onboard sensor to measure the surrounding vehicles, and we also have external physical environment. And if we want to achieve the efficient and safety in our CAV system, so the two components need to work closely with each other and operate each other in a really good manner. But in a typical cyber physical system, we also have a disturbance from the physical side and also from the cyber side. For example, in the physical side, we have abrupt cutting maneuver, and in the cyber disturbance, we have a communication cyber attack. And the communication cyber attack, which means the hacker, they try to manipulate the V2V information and to disturb the CAV operation. Because once they use those kind of manipulated data, they will generate a misleading control demand or something. They will finally lead to reduced CAV operation efficiency and also compromise the traffic safety. So in this study, we're gonna focus on the communication cyber attack part, but we also gonna touch a little bit about cutting maneuver because we are talking about a multi-lane highway. And in the cyber attack or the cyber security using transportation system, we can broadly categorize into two parts. The first one will be the abnormality detection. The idea in abnormality detection is I try to label which information is false information and which is reliable or trustworthy. And then I gonna know which information I gonna use for my control and which I want to drop them. In this part, in anomaly detection, we have a model-driven approach. For example, the very classic one would be a Kalman filter and its variants. And we also have a machine learning base, like one class SVM, also have a deep learning base, convolution network, and the GAN network. And on the other hand side, we have a control strategy. Control strategy, they don't directly pinpoint which information is attacked or manipulated. They just want the control can handle such a noise in the environment. So we can also broadly categorize then into adaptive control, robotic control, and also adverse reinforcement learning-based control. Both approaches are perfect. It's not perfect. It's really good, but they are largely fragmented. So the idea of this paper is like, can we really combine them together? Can we really integrate them together and just let them work with each other? So before we dive into detail, I want to talk something more about the CAV perception. The CAV perception, we actually have a two system. The first one will be the onboard sensor. We use onboard sensor to measure the surrounding vehicles. And other one will be the V2V communication that we share the information with each other. So imagine that in the scenario where the measurements are assumed to be perfect, then any difference between the measured data and what communicated can be a clearly indicator of communication cyber attack because we already have a reliable benchmark, which means measurement. Measurement is reliable. Luckily, we do have some okay sensor in the current technology. For example, like in the current autonomous vehicle, we have a multi-sensor, LiDAR, radar camera. We also have a advanced data fusion algorithm try to have a reliable estimation from the surrounding environment. But sensor is not perfect, of course, because they always have a noise inside. And we can go to touch a little bit of V2V communication. Why we want to have a V2V communication? Because we want to support the control objective and improve the traffic across multiple perspectives. This is what I'm talking about, for example, efficient, safety, and a lot of things. And if the V2V communication is 100% accurate, of course, we want to fully leverage this information to maintain a robust and reliable operation. However, it's not just like a cyber attack. But even when we recognize the half-truths are aligned, we still try to find the truth hidden within it because there are so many information within the V2V communication. We want to use them for our control. How are we going to do that? How are we going to play with the V2V communication, the measurements, and also control? And we found out like actually we want to address this issue in this study. We try to combine these three components together to address holistic interconnect CAV system under a cyber attack. And we try to develop an integrated approach that combines the V2V communication, onboard sensor, and detection into a holistic framework for the multi-LAN CAV control. And the detection also serves as an additional layer mechanism, ensure that even under a communication cyber attack, the CAV can still perform really well. So let's go to the methodology part. And in this study, we assume like 100% CAV environment. It sounds really future, I know, but yeah, cyber attack is also really future. Yeah. So if we have a multi-LAN highway scenario, we can easily have a time variable measurement graph. So as long as the vehicle within the perception range ahead of the LAN direction, same or adjacent LAN, and consider a LAN of site sensing constraint, and we can have the adjacent matrix built for it, and that would be the one. And we also have a reliability matrix over here, which indicate the reliability of the onboard sensor. In this study, we assume that onboard sensor is reliable. So that will always the matrix here will be always be 1. And following the same philosophy, we can also build up the time variance V2V communication graph. As long as the vehicle within the communication range and share only upstream and the information only shared to the upstream CAVs, we can also have this like a communication graph. And the blue element here is the example of the CAV2 over here. So we can know that, but different things is that the reliability measure here is not always be 1 because there might be potential cyber attack. Ideally, we want the reliability reduced to 0 when there is a cyber attack, so the CAV can reduce the weight on using such information to generate our control demand. And how are we going to achieve these goals? And before we dive into detail, I would like to define some state in the following duration. The state of CAV is defined as the position, velocity, and acceleration. And the measurement state, which means the relative state of the CAV I and CAV J. For example, the spacing, the delta V, and delta A, and also the measurement angle. And the communication cyber attack is modeled as the addictive noise in our V2V information. And you can see from the below equation over here. So let's talk a relatively easy case, which means reliability evaluation between an ego CAV and its measurable and connected CAV. Here will be the example, like the purple vehicle over here, XIJ, CAV-IJ and CAV-IJ -1. So I can measure the relative state of the CAV-IJ -1. I can also receive the information from CAV-IJ -1. So if there is a no cyber attack, we're gonna know the deviation from these two sources gonna follow the measurement noise distribution. And if your measurement is reliable, then they will normally follow the zero mean Gaussian distribution. However, if there is a cyber attack, the deviation from two sources is gonna be really significant, and that will be so the difference might not follow the measurement noise, which means the zero mean Gaussian distribution, because we have additive noise inside. Then we need to find a matrix to describe such a distance. So we adopt the Mahalanobis distance to measure how far the sample line from the multivariate distribution. And this distance follows the calculated distribution. So we can adopt the upper tail calculated test and use the p-value from this calculated test as the reliability. And the reliability is actually evaluated by CAV-IJ for the information received from the CAV-IJ -1 at time t. And then there's a tricky case that what about how to estimate the reliability between the ego CAV and it's not directly measurable but connected CAV, because we still need to use their information. So we use the distributive evaluation, which means each CAV gonna locally access the reliability of the measurable and connected neighborhood using onboard sensor. And then the ambient direct measurable CAV get reliable along the communication path, which means this, for example, here, the blue vehicle gonna share its information to CAV-IJ +1, and the ij plus 1 will estimate its own reliability and share with the CAV ij. So by that case, the estimated reliability will also share through the V2V information. And once the CAV ij got all of the estimated reliability, we can just multiply them all together, and we got a final result. And here is a case. For example, we have the leading vehicle, the black vehicle, share its V2V information to the purple one. Based on the measurement graph, we can actually find the 5 possible evaluation paths. 1, 2, 3, 4, 5. And each path will give us the different evaluation score to describe the same information that's shared through V2V communication, which means the black vehicle to the purple vehicle here. And the next question, because right now we have so many like evaluation score, and they actually evaluate the same thing. How are we gonna combine those kind of multiple evaluation results to generate the one more accurate one? Here we borrow the evidence theories, or you can also call it Dam-Schaeffer theories. The Dam-Schaeffer theories is they actually combine the multi-source and have one unified and robust estimation. And this one unified robust estimation gonna put in our reliability matrix to determine the weight of using such information in our control algorithms. And evidence theory can reduce uncertainty, they can provide more accurate estimation, and there is no prior knowledge required. And each score is turned into the belief mass function supporting the reliable, unreliable, or even I don't know information in our evidence theories. And normally, we need to combination rule to combine the different sources. For example, like disjunctive rules, we actually preserve the uncertainty whenever any paths disagree. We also have a conjunctive rules. They actually concentrate the belief when all paths agree. So we also have a term called conflict here to measure the disagreement among evidence, among the sources. But there is an underlying assumption for disjunctive rules, like they assume at least one V2V information is reliable. And for the conjunctive rules, they assume all shared V2V information are reliable, which is quite tricky here because we don't really know if they are reliable, right? So we propose the robotic combination rule over here to adaptively balance between the conjunctive and disconjunctive rules. Our robotic combination rules, they will blend the two extremes, leaning on agreement when the conflict is low and on uncertainty when conflict is high. Here is an example in here. So M1, which means one pass, and M2 is in the second pass. Only when paths are highly consistent and indicating the low conflicts and agree that the V2V information are reliable, which means this point, and which then the final estimated reliability will also reach to 1, which means very reliable. So by that way, we can somehow got our final unified evaluated reliability over there. And we're gonna combine this evaluation into our control algorithm because this is for multi-lane CAV control. So we also consider the lateral movement here because the lateral movement under a cyber attack scenario is highly possible to have a forced lane changing behavior. So if adjacent vehicle near our lane, we form 2 virtual platforms over here. One assume the cutting happened, another one assume the cutting does not. Each virtual platform generates its own control recommendation or control demand when we scale each demand by its fused reliability weight. Low weight mute the scenario and high weight engages fully. This ensures the vehicle reacts proactively to trustworthy lane changing signals while ignoring those suspicious and low confidence data. And so by that way, for the lateral control, we consider reliability. For the longitudinal control, we also consider reliability based on the estimated reliability. And the reliability also comes from the multiple source, which means the multiple evaluation path. And then we're going to introduce something about experimental results. In these cases, we use the leading trajectory from NGSync, and we also have several comparison candidates We have ACC, adaptive cruise control, which means I don't trust V2V communication. I just use my own measurement. And we have a CACC without evaluation mechanism. We have a CACC-S, stand for the single path evaluation, which means I only evaluate my immediate preceding vehicles. I don't evaluate the vehicle in the adjacent lane. And we also have a CACC-M, which stands for the multiple path. And because in this study, we used a distributed evaluation, so it's also possible that the hacker will just attack the estimated reliability. So rather than the normal vehicle state attack, we also consider reliability estimates attack, and the result will show in the following. The first of all is the following cases, a no communication cyber attack. And in the table, we use the ACC as a benchmark and to compare the relative performance with the other controller. And we can see that the evaluation mechanism will not affect the normal operation of CACC over there. And of course, the CACC generally perform better than ACC. And in the more complicated cases over here, and the CAV7 will have a vehicle state attack, and CAV8 will have a reliability attack. So because the CAV8 have a reliability attack, so all of the information shared by CAV8 will be assumed will be reliable, but actually they are not. So in these cases, if we check the CACC here and CACC-S, because we rely only on single path, the performance is significantly decreased. But our CACC multiple paths, because we do not rely solely on one path, longitudinal path, as long as there is an untagged evaluation path, it still perform well. We can also see the right-hand side over here. This is the no cyber attack cases, and this is the case of CACC-M. This is basically remove or drop all of the impact from the cyber attack. And in the communication layer, it's the same. They basically reduce all of the noise injected by the hacker in the communication layer. And we also have the worst cases over here, which means all of the surrounding vehicle was being hacked. You can treat as a CAV9 over here. All of the surrounding vehicle was hacked. I don't have even one reliable path to evaluate it. But luckily, because we build up a graph based on the time variable measurement and the communication, as long as there is when the vehicle layout change, for example, here there is a one plateau joining the communication graph, it's possible to have a new path that provide a reliable result. For example, the CAV9 can evaluate it can evaluate CAV7 through 9, 17, 16, and 7. So we know even in the worst case, as long as the layout change, we still have a chance to reduce the impact from cyber attack. And this is we also have a lane changing cases. For example, false lane changing. In these cases, the CAV15 will share the information that, okay, I'm gonna change the lane, but actually I'm not. For the CACC, there will create a valve, but for the CACC-M, we're gonna close the valve and improve the efficiency. And in other cases, like I tell the other autonomous vehicle, say I'm not gonna change the lane, but I gonna make the lane change. So in this case, they will have a near missing event over here, but in the CACC-M with a better anticipation, they will not have a near missing. They will improve the safety. So the conclusion, the CAV is a system of systems, which each component should jointly consider, and each component have a potential alleviated disturbance from other components. And we also implement the DF theorem with the robotic combination rule to generate the dynamic reliable sources. And we also propose the reliability weighted multi-agent control, design and validate a distributed CAV control algorithm, and ensure the coordinated resilient CAV behavior under a cyber attack. And future work, because in this study was similar onboard sensor is reliable, but in the future, we will consider use the, for example, Kalman filter to enhance the reliability of the sensor, and also consider mixed traffic. And because the mixed traffic will also provide a difficulty in the measurements, since human-driven vehicle cannot really perceive the surrounding environment and share the information with the other autonomous vehicles. Yeah, thank you. Any questions?
See how I think we're short on time, so questions, we're gonna drop them in the chat box
No
right
problem.
there. Thomas, thank you so much. Very interesting work. Thank you everyone for joining us. I hope you enjoyed as much as I do, and we look forward to meeting again in similar fashion in other conferences. Thank you so much again. That was really a resource for special session. Thank you all. Have a good day.